Section 3.2 has the composition of one function after another and ideas about what it means for a function to be invertible. Let's go. So if we've got two functions, one going from x to y and then one going from y to z, then the composition is defined by following the values through the functions. So it's written like this: g and then a circle f, and that's pronounced g composed with f, or possibly I like to say g after f. You'll see why in a second. G after f, that's a function from x to z, and it's defined by, so here's the function applied to a particular value of x. I suppose that value is in x, and the rule is that first apply f to get to something in y, and then apply g to that to get something in z. So you follow through the arrows, x goes to y and y to z, and similarly the value lowercase x maps to a value f of x, and then f of x maps to, let's call it y over here. Y maps to g of y. So I'm calling y equals f of x in the middle here. X maps to f of x, y maps to g of y. So you do the mappings one after the other. And that's why I pronounce it g after f. I'm going to do that throughout this video, I think. So that's the way I say it. I have a comment that the order matters, and it's pretty hard to see how you could think that the order didn't matter. It's pretty tough because up here the definition involves three sets, x and y and z. So first problem, y is supposed to be the same in the middle here. So if you want to talk about f after g, well, f after g would be you take an element in y, you map it to somewhere in z, and then you've got this function that takes values in x, but I'm not in x, I'm in z. So the only way that they could simultaneously be just defined is if x and z are the same set. So if f takes values from x to y and g takes values from y to x, okay, now they're at least defined, but new problem, g after f is a function from x to x now, in the world where x and z are the same, and f after g is a function from y to y, because f after g means it's expecting to be given a value in y. So the only way that those are going to have the same domain as each other is if, in fact, x is equal to y. So if you want these things to be the same, then just to get off the ground, you need all of these sets that I'm talking about to be the same set. And even then, I haven't talked about the values yet, and bad news. In general, even then, if x and y and z are all the same set, then you don't get the same values out. I have an example, but to be honest, I don't know why you'd expect to get the same values out. So you can pick almost anything. I've gone for squaring and exponentials. They're both maps from reals to reals, but if you do f after g, then you get e to the 2x, and if you do g after f, then you get e to the x squared, which is not the same thing at all. So it is possible to get the same function when you change the order, but for now, it's safer to assume that you get something different. Okay, so order matters. We're going to pronounce it, if it's written like this, as g after f, to remind ourselves that we're applying f, the function, first, and then the function g. I suppose the reason it's written this way round is because probably when you met function composition with this notation, you wrote it like this with nested brackets, so that the g appears to the left of the f, even though, well, maybe up here you were hoping that I would say f then g, because they kind of glue together in that order, look, left to right. Sorry, in order to be consistent with the way that this is written, people define this notation this way round, g after f. Good news though, this means that if you want to apply this function to a particular value of x, you can kind of just write brackets instead of composition circles and then get the thing you're expecting. So it's sort of consistent notation, but somehow still confusing notation. Oh well. Right, what would I like to tell you about this? You can't switch around the order, but function composition is associative, which means that if I've got three of them, so functions f, g, and h, I need four sets now, so f from x to y, g from y to z, and then h from z to w. W is the traditional letter to use if you've just used x and y and z. Suppose that those are three functions, and I want to do, well, sort of the obvious composition. I want to follow a value from x to y to z to w overall. Then good news, the function that's made like this, f after g after h, that's the same function as f after g after h. I have to pause there to try and pronounce the brackets, and because if I say it out loud in words, I'd probably say f after g after h, in which case that sounds like both of them. Good news, they're the same function, so I am allowed to say that without pausing, and I'm allowed to write it down without brackets, but that needs a proof. And the proof is pretty simple, really. The idea is that when you take a value of x, the thing that you're calculating is this. When you apply it to a particular value of x, f of g of h of x. And the rest of this line is just interpretation to say, if you look at it one way, then this is g of h in the middle. So I've written g after h to indicate that I've recognised that inside these outer brackets, it's a thing I recognise, it's g after h. Oh, and then I suppose that's f after g after h. But looking at it differently, maybe you see these things, and you say, well, I recognise what this is, it's f after g, and then with something weird inside that I haven't looked at yet. So I'll write f after g applied to h of x. Oh, but then that's f after g after h. So you can build up these interpretations of this expression in two different directions and end up at these two different expressions, which, because this is true for all x in the set x, these functions are equal. So good news, function composition is associative, which means that you don't have to worry about where the brackets go when you do this. Okay, we're going to break this down. We've got a big proposition on the screen. I'd like to think about how the properties of f and g affect the properties of g after f. So if I've got a function from x to y and then a function from y to z, I might be interested in what can I say if both of those functions are injective, or what if they're both surjective? And conversely, the other way, what if I know the composition is injective? Can I say anything about the functions I started with? What if I know that the composition is surjective? Can I say anything about the functions I started with? The truth is quite complicated. So good news, if your functions are both injective, then so is the composition. If the functions are both surjective, then so is the composition. Conversely, you get a kind of partial result that if the composition is injective, then f is injective, but g need not be. And if the composition is surjective, then g is surjective, but f need not be. So there's about 6 different claims on the screen at the moment. I'm going to show you some proofs of some of them, but I want to be clear about how I'm splitting this down into separate parts. So just looking at that first part I think the claims are, if f and g are injective, then so is g after f, and then separate claim. If g after f is injective, then f is injective. That's a claim, needs a proof. And then finally, g need not be, where the conditions for this last bit are if g after f is injective, then g need not be. So that's 3 separate claims. We're going to prove those one at a time, and then I'm leaving part 2 as an exercise for you to try something similar. Okay, So here's that very first part. I've just cut down the text on the screen to show you that first part. If f and g are injective, then so is g after f. So reminder, for injective functions, that means that whenever f is injective, so whenever f takes the same value, it had the same inputs. So for this part of the proof, we are supposing that that property is true for f and also for g, and we're interested in what happens for g after f. In particular, we're interested in what happens if the values of g after f agree. And this is just algebra. You could maybe draw a picture or something to try and chase through with some arrows what you think is happening. But when it comes down to it, I think the best way to prove it is to just write down some algebra. So here's an attempt. Suppose that x1 and x2 are in x, and that, when I did g after f, I got the same value out the end. My aim here is to convince you that x1 is equal to x2. That's the definition of injective. But what does this actually mean? G after f means that we applied functions g and f, not in that order. So g after f, that means this. And since g is injective, so here we go, we've got some facts that we can use. We deduce that f of x1 is equal to f of x2. I can see here, if I squint, g of something is equal to g of something. Injective means that those somethings must be equal. And then since f is injective, we can go one step further and say, aha, this is exactly the thing in the definition of injective. F of x1 is equal to f of x2, so it must be the case that x1 is equal to x2. I've got back to where I wanted to, so g after f is injective. So this is an example where I'm sort of 1/3 of the way through 1/2 of the proposition, but just by focusing on this part and remembering which definitions I can use right now in this part, I can step through the lines without trying to do all three things in my head at once. Okay, let's do another one. So we've seen here, if f and g are injective, then so is g after f. I'm also interested in the other way round. So what if I tell you that g after f is injective? The idea is we want to show that f is injective. And we're limited in the information we've got this time. Previously we knew that f and g were both injective, but now we just know that g after f is injective. And our aim is to show that f is injective to prove this. So optimistically, I'm going to start writing down what it means to be injective. I'm going to suppose that f of x1 is equal to f of x2, confidently hoping that I can end with the deduction that x1 is equal to x2. And I can't go straight there. I have this fact about g after f, and at the moment on the page I've written out this much. So I need g after f to appear if I'm going to use this fact. So that gives me the idea to apply g to both sides. If I do that, then I get g after f of x1 is equal to g after f of x2, and now I can use the fact. Because in this case, I'm told that g after f is injective, so we can deduce that from this one, that x1 is equal to x2. And that's a single line deduction this time round, because in this world, we know that g after f is injective. So I'm viewing all of that as a single function, a function where I know a fact. I know that that function is injective. And I can see it on both sides. Because the function is injective, essentially I can remove it from the outsides to tell you that the insides, x1 and x2, are equal. So that's a demonstration that f is injective in that case. For this last part, we're just trying to find out whether g needs to be injective. We're trying to prove that it need not be. And the idea there is, well, I've got to explore and find a counterexample. Here's one that I've found. And the idea is that, well, g could be up to all sorts of other things. We've seen that f has to be injective, but g has got all of the set y to play with. So extreme example, if I take g to be very not injective, to take lots of different real numbers and map everything to 0, then my function f could be something pretty simple, which only returns a single number there, but then g is not injective because it's mapping loads of things to 0. So I can set this up so that g after f hardly refers to any numbers at all, any function activity, but g is doing lots of other stuff. So that g after f, sure, that might be injective, but g has got this wider life of things going on. Okay, so extreme example, x and z, both the set that just contains 0. That's a kind of token effort to set up functions from x to y and y to z, just by taking them to be 0 goes to 0 in both cases. But for that function from y to z, I also get lots of other stuff that I can do. I'm sending everything else to 0. Then g after f is a pretty basic function. It just takes 0. Ooh, that should be a z. It just takes 0 to 0, but g is not injective. It takes loads of things to 0. Okay, so splitting down a proposition into lots of little parts. Part 2 is an exercise for you to check what's going on with surjective functions. You'll need to remember the definition of a surjective function, of course. Okay, so I want to talk about invertible functions now. Cases where there's an inverse. Let's define that. So a function from x to y is invertible if there exists a function g going the other way from y to x, such that this composition is the identity either way round. So g after f is supposed to get you back to where you started. That's the identity function, the function that takes x and gives you the same value of x back again. And also f after g is supposed to be the identity on y, so that any value of y, if you do f after g, then you get back to the same value of y that you were looking at. If that's the case, then we say that g is the inverse of f, and we write g as f to the -1, which is maybe not the best notation, but it's what people use for inverse functions. You've already seen symbols used like that for pre-images of a set, and it's important that we don't mix the two up. Okay, I've said the inverse. I should justify that, because how do I know there aren't two? How do I know that your function doesn't have multiple functions g that do this? And I have a proof for this. It's a uniqueness proof, which means I try to prove that something is the one and only. It works like this. Proposition at the top: if the function from x to y is invertible, then its inverse is unique. You will see quite a lot of uniqueness proofs in a mathematics degree. The structure that I recommend is suppose that there are two of them and try to show that they're equal. So suppose that there are functions g1 and g2 for which g1 composed with f is the identity on x, and also g2 composed with f, and simultaneously f composed with g1 is the identity on y, and also f composed with g2 is the identity on y. So they both meet the definition. So using the fact that composition is associative, and that's good because it lets me glue together some of these things that we've got. We have things like g1 after f, and I have things like f after g2. So maybe we can make something of that because we know facts about that. In order to use that, I'd like f in the middle, g1 on one side, g2 on the other side, and then importantly, it's just this middle idea is the important idea, that you can interpret that function in two different ways. On the one hand, g1 after f after g2 means that you do f after g2 and then you do g1. On the other hand, it means you do g2 and then you do g1 after f. Breath indicating brackets. Right, okay. We've got some definitions that say g1 after f is just the identity. So this composition is you apply g2 and then you leave things alone, that gives you g2. And on the other side, this composition is supposed to be the identity on y. So we have the composition leave the leave the element alone and then do G1 to it. And that's just G1. So this shows across the whole line that G1 is equal to G2, but it's another proof where the idea is in the middle and there are two different directions to rearrange things to eventually show that two things are equal. So this shows that the inverse is unique. If you have a function and it's invertible, there's only one way to invert it. This gives me one of my favourite examples in these lectures, which is a non-trivial example of a function. We've seen several functions here. Most of them have been defined on numbers, but functions can be defined on any sets, x and y. So here's my example of a non-trivial function. Let x and y be sets, and let f be the set of all invertible functions with domain x and codomain y. So that could be quite a lot of functions from x to y, and I'm thinking about those functions as forming a collection, a set of objects. In this case, every element of that set is a function, and they're invertible. So that means for each one there, you have an inverse, which I can write as a function t from the set f to the set f, such that t takes each function to its inverse function. The proof that we just worked out to show that there's a unique inverse demonstrates that this is well defined, that for each function there is an inverse function. Well, there is an inverse function because I'm only talking about invertible functions, and it's a unique member of the codomain because the inverse is unique. Here's the mind-bending bit. That function t from f to f is its own inverse, because t after t is the identity on the set f of functions. That's a fancy way of saying the inverse function of an inverse function is the function you started with. The proof of that is pretty hard to write down because it just looks like the definition. Function and inverse function are supposed to give you the identity either way round, which of course means that if you're holding inverse function and you're looking for some function that might be the inverse of that, well, f itself will satisfy both definitions. They were already in front of you in the definition of f inverse in the first place. So the inverse function of an inverse function is the function you started with, and written like this, that tells you that t is its own inverse. We have a function on the set of functions with an inverse function on the set of functions that is itself the identity. Yeah, right, brilliant. Okay, t after t is the identity on f. Good, right, okay. Sometimes I think all the examples of functions that we put in these lectures are, just squaring and rounding up numbers. And I want to give you an example where the sets are pretty weird to start off with as well. Result here. If you've got a composition, I would like to show you how to invert that. So setup, I've got to explain that you've got sets x and y and z, functions f from x to y and g from y to z. If f and g are invertible, then good news. G after f is also invertible, and the inverse is f inverse after g inverse, which is maybe a little bit annoying, but you've met this before, of course. When you put on your shoes and socks, you put on the socks before the shoes. So f is putting on socks and g is putting on shoes. And then the inverse of that, to take things off, you take off the shoes before you take off the socks. You do the inverse operations in the other order. Let's demonstrate this with algebra and try to move away from the shoes and socks example. The thing I need to check is that this function that I've written down here really is the inverse function for g after f, the composition. To check that, I need to make sure that the composition, either way round, gives me the appropriate identity function. To make sure that if I do this and then that, I get the identity on X. And if I do that and then this, I get the identity on Z. Yes, good. Okay, let's go through that step by step. So I've written this out using associativity lots of times. I'm not sure why I bother writing out so many brackets. I guess I like demonstrating exactly where associativity is taking place, but it works like this. So here I've got F inverse after G inverse on the left, after G after F. But associativity means that I can take this set of brackets and move them over to the others. So I'm thinking about this as being a single object over on the left, and moving the brackets over. That's how associativity works. You have 3 objects. It's a little bit confusing because I obviously have 4 objects on the screen here, but thinking about this in brackets as a single object, I can move those other brackets over here. And then inside here I've got 3 objects, so I can use associativity in there. And then I've got, by definition of G inverse, I've got the identity on Y, and then things simplify nicely as F inverse. And I get back down to the identity on X, using all the properties that I've got along the way. And the other way round, if I put F inverse after G inverse on the right, then again, following through associativity to move these brackets over there, and then inside those brackets to shuffle things around, and then use lots of definitions, I can get down to the identity on Z. Those are the properties that it needs to be the inverse of G after F. And I apologise that this proof doesn't contain any shoes or socks, but that is how I think of it. So there you go. Right, final thing to say about injective functions, which maybe you've already noticed, which is that they're the same thing as bijective functions, and that a function from x to y is invertible if and only if it's bijective. So reminder, invertible means that there is an inverse function, and bijective means that it's both injective and surjective, where injective meant that values never collide and surjective meant that you hit everything in the codomain. So proof is going to go both ways to demonstrate that if we're invertible, then we can get both the properties over there, and that if we're bijective, then we can get both the properties over here. So there's quite a bit of work to do. Let's go. So first, suppose that f is invertible, which means it has an inverse function that goes from y to x. Okay, we aim to show that we're injective and surjective. So let's do the injective bit first. Like normal, suppose that we have x1 and x2 such that f of x1 is equal to f of x2, then, well, we're armed now with a proper inverse function, which is supposed to get you back to where you were before. If you apply the inverse function after f, then you get the identity. So applying it to both sides, we have over here, if I apply it here, then I'm describing x1 maps to f of x1, and then maps to the f inverse of that, which has to get me back to x1, that's the definition of an inverse function. And on the right hand side, same story, but with x2. So the inverse gets us back to x1 and x2. It undoes the application of that function. Or if you prefer, very algebraically, this is one of the things in the definition, and I'm using it in here, where I have some equality from the previous line, and now this function composition is the thing in the definition. So f is injective. And then to show that f is surjective, I need to check that every value in the codomain has a pre-image in the domain. So take some value y in the set y, and note that f inverse of y is f inverse is a function defined on y, so it has to take a value in x, and that value in x is then good enough. The whole point is that when you apply the function to that value, that composition is the identity on y, so you'll get back to y. And that means that f is surjective for every point in y, just the fact that this function exists and does the thing you want. Therefore, f is bijective. I'm sorry that I'm hiding half of the word bijective. Hopefully you can infer. Never mind. Okay. Going the other way, I suppose that the function is bijective and my aim is to show that it's invertible. So going in the other direction, because this is a statement of the form if and only if. In the other direction, I'm going to assume that I'm surjective and injective and try to show that there's an inverse function, which means I need to build the inverse function and tell you what values to take. And of course, I'm not going to do that with a recipe, like trying to explain square roots. I'm going to try to convince you that such a function exists. So this is maybe not quite constructive to give you a concrete example, but here we are. Okay, so suppose that f is bijective. We're trying to show that there is a well-defined g going the other way from y to x, such that when you do g after f, you get back to the value you started with, and if you do f after g, you get back to the value in y that you started with. Those are different things. Since f is surjective, that means that for any y in y, there really is a pre-image. It might, at that point, you know, we've been hurt by surjective functions before, we know it might not be unique, but actually because it's injective as well, we know that this pre-image is unique. Because if there were two, we would have f of x1 is equal to f of x2, and then we would say, aha, x1 has to be equal to x2. So we have a unique pre-image. Good news, we're going to set that to be the value of our inverse function. When you show me the value y, I'm supposed to go and find this unique value in x. I know it's out there, I know it's unique, such that f of x is equal to y. And just to spell it out one more time, I know that there is such a value because we're surjective, and I know that it's unique because we're injective. And that's what I need to be a function. I need exactly one value. Okay, so for each y, there's a unique x, and this recipe gives you a well-defined function. We'll call it g, so that g of y is equal to x. Precisely that value of x, such that f of x is equal to y. And then composition just works really nicely because these things go, one goes one way, one goes the other way. So following it through, g of f of x is g of y, which is x, and f of g of y is f of x, which is y. So it sticks together really nicely there. So g satisfies both properties that you need to be an inverse of f, and therefore f is invertible. We've sort of found its inverse function. Hopefully this helps convince you that such a thing is unique as well. We didn't get any choices along the way when we were building this inverse function. There's only one if your function is invertible. Okay, so that's a proof that bijective functions are invertible and vice versa. You might have noticed along the way that, well, being invertible means that you have to satisfy two properties, and being bijective means that you have to satisfy two properties, and we used them one for each. So for this first bit, we used this identity on x fact when we were talking about f being injective, and we used this identity on y fact when we were talking about f being surjective. And going in the other direction, we had this idea about the function needing a value that is a unique value, and we used injectivity and surjectivity, one of each there. So you might be pleased to know that you can formalize that with ideas about left invertible functions and right invertible functions, where you split the definition in two. So a left invertible function f from x to y is one where there exists a function g such that g after f is the identity. That's half of the definition of an invertible function. And a right invertible function is one with a right inverse h, such that f after h is the identity on y. So in that case, you can start with any value in the codomain, find something in the domain, and then apply f to it and get back to where you were. You'll be pleased to know that splitting this definition in half matches up perfectly with what happens if you split the definition of bijection in half, by which I mean that a function is left invertible if and only if it's injective, and it's right invertible if and only if it's surjective. The proof of that is left as an exercise. Hopefully you can piece together the definitions and the proof that we just saw about bijective functions, where we did both. I suppose I'm suggesting that you take half the definition, half the target, and use half of the proof to get there in each case. Can you split everything perfectly into a sort of partition of the definitions and the proofs? Right, okay. So that takes us to the end of the section on functions. There's one chapter left where I would like to prove a few more things, go through some problem solving techniques with you, and also show you just a few more exercises and proofs. I'll see you in the next video.